For the next probability distribution, I'd like to do the Poisson distribution. So we have the notes here, and I have the basic definition. X is the number of events which occur in a fixed homogeneous interval with mean rate lambda equals number of events divided by interval size. That's the definition, and it's a good one. And the support is x equals 0, 1, 2, and so on. Notice that it's an infinite support. This does differ from the binomial probability distribution, and I'm going to try to sketch that out a bit. Let's consider what Ugarte, Militino, and Arnhold say. So I want to go over to their book, page 120, and look at their derivation a little bit. Okay, so in a little more detail than the definition I have concisely stated on the handout, it's going to talk about a thing called a Poisson process. Okay, notice the parameter lambda here, okay, is a non-zero parameter. There's three conditions. You can determine if something follows a Poisson distribution if it satisfies these three conditions. I'll distinguish the distribution and the process in a little bit. Okay, so the first one is your scenario has non-overlapping intervals that are independent. Okay, I'll talk about the possible cases in a little bit, but for now you could think of it as time. Okay, given a span of time, each fixed interval can be broken up separately, and the number of events in the first interval is independent of the number of events in the second interval. Number two, okay, the probability of two or more outcomes in a sufficiently short interval is virtually zero. So it doesn't matter how big it is. Once you get it short enough, you're either going to have one event or no events. And then the third, the probability of exactly one outcome in that short interval is proportional to the length of the interval. Okay, so as it gets longer, it's more likely that you're going to have an outcome occur. Okay, and it's directly proportional there. So we show it like this: lambda times h, referring to the interval. Okay. Now, so according to our book, and note the page here, the resulting random variable x is called a Poisson random variable, okay, if it satisfies those three conditions. Now, here's the probability mass function, and we'll hold on that because it appears mysterious. It's got the natural log in it, like, wow, where does that come from? Let's talk about its derivation. Okay, so let x be the number of outcomes in an interval of length 1. Okay, so t here is just the length of the interval, so we're going to fix that as a length 1. You can see this is arbitrary, and we like it that way. Okay, great. Now, to find the probability that x equals x, we're going to take that length 1 and we're going to cut it and put it into n subintervals. Okay, so of this interval here, we're just going to go ahead and cut. So cut, 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 cut. Okay, this would be a case of n equals 5. So instead of being length 1 here, now there we would have 1/5. Okay, provided n is much larger than x, the probability of one outcome in any given interval is 1 over n. Okay, we said that. Now, using the third item, we have probability proportional to length. Then, if the average rate is lambda, that's what lambda is, it's the average rate. Okay, then if we cut the thing into fifths, then the average rate should be lambda over 5. Okay, so what we're going to do then is we're going to take the binomial probability distribution, okay, which we know is n choose x times pi to the x times 1 minus pi to the n minus x, okay, where x is the number of successes in n trials, okay, and pi is the probability of success in each trial. So for the binomial, probability that x is some specific little x, we've got x successes, we have n minus x fails. You can count them this many ways, add that up, that's the probability that you get x successes. Okay, so we're applying that logic now onto, bring it over here, this scenario where my rate of success was lambda. Now my rate of success in the subinterval here is lambda over n. Okay, so we have a lambda over n probability of occurring in the subinterval, and that does it. Okay, do I need anything else? Okay, so yeah, that works. So we're going to take this binomial probability mass function, and we're going to plug into the pi this dude right here. And that gives me the first line. Now, to go to the next move, all we're going to do is we're just going to expand this right here. No big deal. And there's a little move that's going to happen. Let's see, I've dropped my n from the n minus x. Okay, so I broke that into two pieces here. And lambda to the x n over x. Okay, good. So that one's there. Got it. Moving to the next one, this x factorial is going to come out here. The lambda to the x comes out here. Okay. Now on the inside, I'm going to take this n to the x and I'm going to put that under each one of these guys. So that gets us this part right here in the brackets. And then on the right, we drop down. Okay, so just a little bit of expansion. Now here's the argument, and we've got it. X is fixed because we're calculating a probability mass function for a particular x. Boom. Okay, we're going to let n go to infinity and pi go to 0 so that lambda equals n pi remains constant. That's the key piece. And so what are we doing? We're holding the rate constant. And that's what we've talked about in the development of this Poisson random variable, is lambda is some fixed rate. Okay. Now, so it comes from this part right here. You have pi is lambda over n. Lambda is pi times n. And as you'll recall from the binomial, when x is binomial, then its expectation is pi times n. You can check that out. So that seems plausible. Okay, when we do that, then we're going to just take a look. We're going to let n go to infinity, so it doesn't affect this part. Okay, inside the brackets, n going to infinity, 1, 1, 1. Everybody's 1. Awesome. Okay, this guy's going to go to 0. Oh, but we've got the superscript, so we're going to hold that part. This guy here, that's going to go to 0, so 1 minus 0 to a power, that's just going to go to 1. So this guy goes to 1, this guy goes to 1, lambda's fixed, x is fixed. So the only part we're worried about is that part right there. And cha-ching, you probably recognize this expression as n goes to infinity, bingo, is e to the negative lambda. That is how we derive, we usually write it like this, e to the x, but you can see what's happening. Okay, awesome. So what's left is this, and that is the Poisson probability mass function. Hallelujah. Okay, so let's go back to the notes then. Okay, let's see here. Probability mass function. Boom, we got it right here. It's a beauty. And then the assumptions, events are independent. 2 or more outcomes in an interval is essentially 0, and that is an interval, a sufficiently small interval. I should elaborate on that. And you have the same probability of the events occurring throughout. It's homogeneous. Awesome. We won't derive the expectation invariance here. We've got a probability mass function. Now, applications, I said I would get to this. So we've considered it in time, which is nicely thought of as a single dimension. So just some dimension. It's great. It also works in a two-dimensional space. So you could have some square of space. Telephone calls during a time period is a one-dimensional. That's a place that this has been well used. Okay, two-dimensional. The number of bombs per square unit in Hitler's random bombing of London follows a Poisson distribution. Okay, so you can think of bombs are hitting here in this quadrant of London, and if you were to divide it into regions, okay, I'm just putting it into a 3 by 3, then the number of bomb strikes per region is Poisson distributed. Okay, all right. Let's see, number of scattered seeds landing in a square unit. If you drop it from your hand, that's not going to meet number 1. They're not going to be independent, at least within the region right below your hand. On the other hand, perhaps if you are throwing them or you're walking with one of those little seed spinner deals, that might get you the random spread. So it depends on the process that's generating this. If you go into 3 dimensions, let's say number of insects in a given volume of space, maybe. Random event frequencies, number of freak accidents per day, that would go back into time. You're catching the idea. And as you're learning of this, probably for the first time, think of it in distinction from the binomial probability distribution and how these counts are not independent, identically distributed trials, but there's some time or space that you're considering, and you're just counting up how many of those things happened. The support is literally infinite. Okay, there's no limit to the number of them that occur. Whereas in a binomial, it's fixed at n trials. Okay, how many males on Biola's campus own a bike? Okay, so males is the population. We want to take a sample of 100 of them. We ask them, okay, they tell us. So n would be 100. And then you can estimate the proportion. This is different. To wrap up the Poisson, I'd like to consider the example in R. The scenario is that a particular flash drive product has, we'll use lambda equals 0.2 bad sectors per flash drive. Okay, so when you get a new flash drive, then burn. That's the number of bad sectors that you can expect on it. Probably don't have one, but out of 5, we would be expecting one. So X is going to be the number of bad sectors on a drive. Okay, so that's the random variable. And Poisson distributed, well, bad sectors independent of one another. Let's assume that that's a result of the manufacturing process. They don't sort of corrupt the others. They're isolated. Okay, and if we shrink it down to a particular region, within that region, is it pretty much either there's a bad one or not? That's reasonable. And is it homogeneous throughout? Using the same process, that seems reasonable. Okay, great. So, given the 0.2, let's just show the probability mass function. If we wanted to find probabilities using it, we could. And I've got scripts that do this in the same spot that we've been using. So we go ahead and run it, and here's the probability mass function. I went ahead and just used a round of the probabilities. It's the d-Poisson function, okay? And here they are. So we can see you've got 0.82, 0.16, 0.02, And they go to very, very small probabilities beyond that. If I were to look at the p dot x, then there is some non-zero probability. It just doesn't show up when I round to 2 decimal places. Okay, now on the issue of a Poisson process, which I mentioned before distinguishing a Poisson random variable from a Poisson process, typically the Poisson process is when you take the variable and you change the units. So let's consider that we're not considering a particular drive now, but we're going to consider, let's let x equal number of bad sectors in a case of, let's say, 10 drives. Maybe we're buying them in bulk by a case, okay? Well, to get that, what we would do is we'd have to take those 10 drives. Again, we're assuming independence, homogeneous throughout. It doesn't matter that they're separated from each other in space. They each have the same feature, and we're just going to consider all of those regions within which we could have bad sectors. So there's 0.2 per single drive. 0.2 times 10 drives gives us a 2. Okay, so we're going to look at the probability mass function of that one, and here it is. Okay, I've got the probabilities shown explicitly. We can see that it's not surprising the expected value is lambda, and that's also the highest probability region. One has the same, you could look at that numerically, and that's what we've got. For our last probability distribution, we're going to do the hypergeometric, which is our 7th. Now, the hypergeometric big picture is kind of like the background to the binomial, but our population is finite. So there's a known finitude to it. Okay. In the writing about hypergeometric, you're going to read about good and bad, but you could just as well think of success and fail. Okay, same thing. Good and success does not connote necessarily something that's pleasant or happy. It just denotes the thing that you're looking for. Okay, so with that then, here's the definition. Given a dichotomous population, that just means, again, good, bad, success, fail. So, like binomial trials, or excuse me, Bernoulli trials, except they're not Bernoulli. I'll tell you why. Population of objects such that M are good, okay, and N are bad. X is the number of ways of selecting exactly X good ones and K minus X bad ones when you draw a sample of size K. So the support then, X is the number of ways to get the good ones. Okay, it could be 0, could be 1, all the way up to K. Okay, the sample size if you got all good ones, unless there were fewer good ones than you actually sampled, at which case you would be bounded by M. So the support is 0 to the minimum of M and K. Okay, great. So that's what we've got. Now, so it should be 0 up through there. All right. Now, assumptions. Okay, we're assuming that we have M plus N in the set. You can denote that by capital N, which our book does, and it's without replacement. That's where we break off of Bernoulli trials. Bernoulli trials are success-fail, and the assumption in the binomial is probability that X equals X is held fixed throughout the process. When you're going without replacement and you have a finite population, you're no longer fixed. The more you draw out, it keeps successively changing the probabilities. Okay, balls in an urn. The proportion changes as they start coming out. All right, the probability mass function is here, And as we've done for the last 6, I want to give you an indication of where it came from. This could be asked perhaps on a test. So we keep in mind that the total population is n plus m. So let's think of that. And so the total possible ways that things can happen is going to be n plus m, choose k. Okay, so that's the total number of ways to sample k elements. Okay, great. So now that's it. That's the biggest possible. So we want a subset. Well, what bounds our subset? We have sort of 2 features, okay? We're fixing that I am selecting X of the good ones, okay? So we are going to select X of the M good ones. So we've got that there. And not only that, but the remaining k minus x must be bad. Okay, so remaining k minus x must be bad, which means that they're coming from the n. So it's k minus x, choose n. We're using the and rule, or the multiplication rule, in counting, and the order doesn't matter. We just have those 2 groups, and that covers it. So this is it's a counting argument, number of ways to get what we want out of the total number of ways, and that's the probability of x equals x with these conditions. So it's relatively straightforward to derive, but it's powerful. And so moments, again, we're not going to derive it right now, but the moments can be found. Moment generating function, I don't know of one, but I don't know that it doesn't exist either, so I've just written a question mark there. Applications, here's one application that you'll see it used called capture-recapture schemes. So for example, you got a mountain and you're interested in what that population size is. How do you estimate that? Well, there's different ways, but this is one way. You catch 10 deer, okay, and you tag them, and then you re-release them. You go out, and then we catch 20 more deer. Now, we're going to count, of those 20, how many are tagged. Under that scenario, we can use the probability mass function to estimate what the most likely number for the population size is. Why? Because we have k, we know what our sample size is, and we know what m is. Let's say the good ones are tagged. Little n is unknown to us, but we can now calculate the distribution with various values of n and see which probability is most likely. We'll look at how to do that later. For now, I'd like to take a simple example on R, and let there be a population of size 100. We'll think of an industrial process here. Okay, so we've got a manufacturing process. Perhaps this is back to USB drives, like in the previous example. And when out of the 100, 5 of them are defective. Okay, we're a quality control processor. We come in, we say, okay, I want to randomly select 4 of the next 100 items that come off of the assembly line. We do that. Okay, well, what's the probability that we got, let's say, 1 or more defectives? Here we go. Okay, we're going to use d-hyper. That'll calculate us the probability masses for this case. Run it, and I'm going to drag this out. Okay, those are the probabilities. We can see there's an 82% chance that we get 0, and so 1 minus the 82 is going to give us 18% chance of getting 1 or more. Given that there's 5 in the batch, that seems plausible. What if we mix it up? What if there's half of them are defective? Okay, wow. What would it look like then? Okay, here we go. There's only a 19% chance that I don't get any defectives, which means the sum of the other bars is going to be 81% chance that I obtain 1 or more defectives. And so on, we can run through this thing. Now, in closing, I want to just re-emphasize that we now have a set of 7 discrete random variables with their probability mass functions. These are tools in your toolbox. Very, very useful. And so we're going to look in class at how to identify what random variable applies in different situations, and then how to work with them, and so on and so forth. But now you've got that big picture of the key pieces of each variable, including some scripts on how to use them in R.